So in this video we are going to derive an expression for the Lorentz force purely from relativistic considerations. So imagine this is a wire and this wire conducts electricity, and these red dots are negatively charged electrons which move to the left with a velocity v0. Thus there's a current I to the right, and these black dots, they are positive charges, and as viewed from the lab frame they remain at rest. Also the electrons are moving to the left with velocity v0 as viewed from the lab frame, and we want to find the force on another charge or a particle of mass m, charge q, which is moving to the right with a velocity, let us say v, as viewed from the lab frame again. We'll consider three different frames. Say an S frame, which is my lab frame, another frame, say S primed, which is a frame attached to this particle of mass m and charge q moving to the right with velocity v, and a third frame, S double primed frame, which is a frame attached to these electrons which are moving to the left with a velocity v0. The gap between any two successive electrons, let's say that gap is L lab as viewed from the lab or from the lab frame. So this distance, these distances are also L lab, and these electrons, they move with constant velocity in a very orderly manner in such a way that at more or less every instant of time a negative charge is over a positive charge, and therefore the charge density of this and the charge density of this as viewed from the lab frame, they are equal, and therefore this is electrically neutral as viewed from the lab frame. So these distances as seen from the lab frame are all L lab. Now if we want to see what the picture looks like as viewed from the S primed frame, the S primed frame or this charge says that it itself is at rest, and therefore it will not say that there is a Lorentz force acting on itself. What it will say is that it experiences an electric field. Because this is moving and the electrons are moving in that direction, there is a relativistic addition, relativistic velocity addition going on, and therefore these negatively charged electrons, they suffer a Lorentz contraction as seen from this frame. Whereas according to this S prime frame, these positive charges, they are moving to the left. This also suffers a relativistic length contraction as viewed from the primed frame, but the relativistic length contraction between these two, or of the negatively charged electrons as seen from the primed frame, is more than the length contraction of this as seen from the primed frame, simply because their relative velocities will be more. So I can say that E primed, which is the electric field that the primed frame says it experiences, is 1 over 2 pi epsilon 0 r. I'm just using the formula for electric field due to an infinitely long uniformly charged wire. Say that's lambda minus primed minus lambda plus primed, lambda minus primed being the charge density of this. Because this suffers a greater length contraction, this has a greater charge density. This suffers lesser length contraction simply because the relative velocity is less as compared to this. So this suffers a lesser length contraction and therefore has a lesser charge density. So this is the electric field that this charge says it experiences. Alright. So this is equals to 1 over 2 pi epsilon 0 r. Let this charge be, both of these charges, let's say they are capital Q, this being negative and this being positive. So capital Q over L minus primed minus capital Q over L plus primed. L minus primed is the length of this, or the length between the distance between two successive electrons as seen from the primed frame, and L plus primed is the distance between two positive charges as seen from the primed frame. So first of all, let us figure out what L plus primed is. L plus primed, now the distance between these two as seen from the lab frame, these are all at rest as seen from the lab frame. So the frame of this is the lab frame. So we can say it is L lab multiplied by 1 minus beta square, where beta is just V over C. So let me just, I don't want to write this out because I need more space. The proof will be a little involved, so I'll need as much space as I can manage. So just remember that beta is V over C. L lab is the natural length between these two positive charges, or any two positive charges, because the lab frame is the rest frame of these positive charges. What is L minus primed? Let's say that L double primed is the distance between any two successive negative charges as viewed in the double primed frame. That is the frame of the electrons. So L double primed is the natural length. So L minus primed is equals to L double primed times square root of 1 minus, let us say, beta t squared, where beta t is the relativistic velocity of this as compared to this, relativistic velocity of the electrons as seen from the primed frame. So beta t by velocity addition, if we were not using relativity, the relative velocity of this would simply be v0 plus v, but relativistically, using the relativistic velocity addition formula, beta t is just beta plus beta naught divided by 1 plus beta beta naught. I'm just using the formula for relativistic velocity addition. So we know what L minus primed is and we know what L plus primed is. So if we substitute those, we get 1 over 2 pi epsilon 0 r. We can take the q's out and we get here 1 over L double primed square root of 1 minus beta t squared minus 1 over square root of 1 minus beta squared. I think, yeah, I have missed an L lab here. There's a L lab here. L lab multiplied with square root of 1 minus beta squared. Now, we can't take anything common out of these. There's a problematic L double primed here. So what we can do is we can write L double primed in terms of L lab. So we can say that L lab equals L double primed times square root of 1 minus beta naught squared, where beta naught is just V naught over C. Now this is also the formula for relativistic length contraction as seen from the lab frame. The natural length of the natural length of the distance between these electrons is L double primed. So as seen from the lab frame, they suffer a relativistic length contraction, which is given by this formula. I hope I've made myself as clear as possible. So what we can say is that L double prime is just L lab over square root of 1 minus beta naught square. The idea of this proof is very simple, although we need many steps to get to the final answer. So I'll just substitute the expression for L double prime. So if I write it out here, so that's just Q over 2 pi epsilon 0 r. Within brackets I'll have, in place of L double prime, I'll substitute this. So I'll get a square root of 1 minus beta naught squared on top. At the bottom I'll get L lab multiplied with square root of 1 minus beta t squared, where beta t comes from here, minus 1 over square root of 1 minus beta squared. So I've just substituted the expression for L double prime in terms of L lab. So now, again I've missed an L lab here. So there's an L lab here. So I can take the L lab out of the brackets, and if I do that, I'll get Q over 2 pi epsilon 0 R L lab square root of 1 minus beta naught square. Alright, so I'll need to figure out what this is. So let me do that in a different color right over here. So 1 minus beta t squared. So 1 minus beta t squared is just 1 minus beta plus beta naught squared over 1 plus beta naught all squared. So let me do that mentally if possible. So I think if I do the square root also, in the end I'll get a square root of 1 minus beta naught squared times square root of 1 minus beta squared divided by 1 plus beta naught. All I've done is I've done the LCM here. The two beta naught terms have cancelled out, and I've got a minus beta squared over here, minus beta naught squared over here, a 1. So this is what we get after this has been done. Alright. So if I substitute that in here, I'll get a square root of 1 minus beta naught squared times square root of 1 minus beta squared, and at the bottom I'll get a 1 plus beta naught. So I'll write that out on the top here, minus 1 divided by square root of 1 minus beta squared. So a few things will cancel out, these two things will cancel out, and I can take the square root of 1 minus beta squared common, and at the top I'll be left with a beta naught. So my final result is 1 by 2 pi epsilon 0 r L lab. Note that the answer I'm getting is in terms of L lab. That's very convenient. Beta naught divided by square root of 1 minus beta squared. Alright. Now this is just the electric field. If I want to find out what the force is, I'll just have to multiply it with this charge. This is the force that is acting along the y-axis in the y direction, and this is in the primed frame, so this is Fy primed. Now because all the relative motions are happening along the x-axis, there is no change in the y momentum. If I change frames, the y momentum of different particles won't change. So I can say that Fy is just dpy over dt, and Fy primed is the same dpy, the py is the same, divided by dt primed. The time, of course, in two different frames, the times will be different. In the primed frame, which is moving with respect to the lab frame, I'll try to tell you what I'm doing here exactly. This force that I have found out is the force on this charge, but it has been found out in the primed frame. I want to find out the expression for force on this charge in the lab frame. So that is why I need a relation between Fy and Fy primed. So what is the relation between dt and dt primed? By relativistic time dilation, the formula is just dt primed over square root of 1 minus beta squared. This is equals to dt. So if I substitute for dt primed here in terms of dt, I shall get Fy primed equals to dpy divided by 1 minus beta squared into dt, which gives me Fy divided by square root of 1 minus beta squared. So continuing with this, Fy then will just be Fy primed times square root of 1 minus beta squared, and Fy primed is given by this expression. So the 1 minus beta squared, square root of 1 minus beta squared, these terms will cancel out, and I'll get Fy equals to capital Q small q over 2 pi epsilon 0 r L lab times beta naught. Let's just check. Yeah. So if I substitute the expression for beta, which is V over C, and beta naught is just V naught over C, I get QQ over 2 pi epsilon 0 R L lab V squared over C squared. But what is epsilon 0 times C squared? And one more thing, this is not V squared, this is V times V naught. This is V over C, this is V naught over C, V times V naught. So what is epsilon 0 times C squared? 1 over epsilon 0 times C squared is just mu naught. So I get a mu naught capital Q small q over 2 pi r times V naught. But what is V naught? V naught is the velocity of the electrons as seen in the lab frame. So V naught is just L lab over time. Distance over time equals constant speed. So this is mu naught capital Q small q over 2 pi r times V times L lab over T. I've missed an L lab down here below. So these two L labs, they will cancel each other out. And capital Q over time is just the current. Oops. I mean this quantity, the small q is not included. So capital Q over time, capital Q being the charge of the electrons, that over time will give us the current. So I'll get Q naught I over 2 pi r times small q times V. So this is just the magnetic field created by an infinitely long current carrying wire. So VQV. So this is the expression for Lorentz force. The actual expression for Lorentz force is just Q of V cross B. But in this case, the magnetic field that this infinitely long current carrying wire creates, it's perpendicular to the plane of paper and therefore perpendicular to V. And so we get, if we do this, we'll get this expression. So what appears as a magnetic force or a magnetic field to us, or a force created by a magnetic field to us, to this charge, it seems that that force has been created by the electric field. So fields actually transform if we change our frames of reference. So what is an electric field in one frame may become a magnetic field in another. So I'll just repeat what the concept is. Because this charge is moving and these electrons are moving, the relativistic length contraction of this as seen in the primed frame will be more than this as seen in the primed frame, and therefore this will have a greater charge density, this will have a lesser charge density, and therefore according to this charge it will experience an electric field. What we have done is we have found out what that electric field is, and from there we have found out what the force on this charge is in the primed frame. We have converted back that force into the force in the unprimed frame, and we have shown that in the unprimed frame we will see the Lorentz force. But because this charge itself is moving with respect to itself, it will say that it is at rest, and therefore it does not see any V, and therefore it does not see any Lorentz force acting on it. However, it sees an equivalent amount of force due to electric field acting on it. And that electric field force comes because of relativistic length contraction. Note that these two forces are not actually equal. This force and the force here are not actually equal, because these forces are seen by different frames, and the different frames, in different frames we will see different forces according to this formula. However, if we know what the force is in the primed frame, we can convert it back to the force in the unprimed frame, that is in the lab frame, and from there we show that that force equals the Lorentz force. So let that wait for this video.